In 2013, a research lab in Cincinnati grew a carbon nanotube fiber roughly half a meter long. The lead researcher held it up to a camera and, in an interview afterward, called it a step toward the space elevator. News outlets ran with it. Popular Science, Wired, Gizmodo, all of them wrote some version of "We're closer than ever." 12 years later, the longest continuous carbon nanotube fiber ever produced is about half a meter long. We haven't meaningfully moved. The space elevator is one of those ideas that lives in a strange purgatory in the public imagination. Half science fiction, half science fact, endorsed by NASA reports, dismissed by structural engineers, promoted by billionaires, and quietly avoided by the people who actually understand materials science. And the question I want to sit with today is deceptively specific. Not, can we ever build a space elevator? That's a fantasy question. The real question is, if we froze materials science exactly where it is today, in this moment, could we build one? What would it look like? What would fail first? The answer, it turns out, involves a Russian scientist writing in 1895 a NASA program that was quietly killed. A Japanese construction company that has an actual completion date on its website, a former Marine who bankrupted himself trying to build one privately, and a problem with lightning that almost nobody talks about. Let me start with a number that broke my brain when I first understood it. To build a space elevator, you need a cable that runs from the equator to a counterweight about 100,000 kilometers up, well past geostationary orbit at 36,000 kilometers. The cable has to support its own weight against Earth's gravity for the first 36,000 kilometers, and then the centrifugal force of the counterweight has to keep the whole thing taut. You need a material with a specific strength, that's strength divided by density, of at least 48 megapascal meters cubed per kilogram. The strongest steel we make tops at around 5. Kevlar hits about 25. Nothing conventional is even close. Carbon nanotubes, in theory, hit 48. In laboratory single-strand measurements, some have exceeded it. This is why the entire space elevator concept became briefly plausible in the late 1990s. We finally had a material that, on paper, could do the job. But here's the part almost every space elevator article skips. Individual carbon nanotubes are strong. Bundles of carbon nanotubes are not. And that gap isn't shrinking. I met a materials physicist at a conference years ago. I was there for something completely unrelated, who told me the most depressing sentence I've ever heard about this problem. He said, "We've been trying to close the gap between single tube strength and bundle strength for 20 years. We've gained maybe 5 percentage points. At this rate, we'll be ready for a space elevator sometime in the year $2,400. He said it the way a doctor delivers a terminal diagnosis. Matter of fact, practiced. The reason is something called the shear transfer problem. When you bundle nanotubes together, the load has to transfer between individual tubes through weak van der Waals forces. Molecular stickiness, basically. If one tube starts to slip, the whole bundle unzips. Making a nanotube fiber isn't like making steel cable where the fibers are chemically bonded. It's more like stacking pencils and hoping they don't slide. There are teams working on this, cross-linking nanotubes with covalent bonds, growing them in specific patterns, using polymer matrices to bind them. Every one of these approaches trades tensile strength for bonding strength. You gain the ability to make a long cable and lose the raw strength that made nanotubes special in the first place. It's like the world's most frustrating conservation law. Which brings us to the guy who started all of this. In 1895, a Russian scientist named Konstantin Tsiolkovsky visited the newly built Eiffel Tower. Standing at the base, looking up, he had a thought that would echo for 130 years. What if you could build a tower so tall that its top reached orbit? The math didn't work with anything you could build a tower out of. Compressive strength wasn't enough. But he'd planted the seed. In 1959, another Russian, Yuri Artsutanov, refined the idea. Instead of building up from the ground, build down from orbit. A satellite in geostationary orbit, lowering a cable to Earth while extending a counterweight outward. The physics was clean. The materials didn't exist. Then, in 1979, Arthur C. Clarke published The Fountains of Paradise, a novel that made the space elevator famous. Clarke was so confident about the concept that he famously said the space elevator would be built about 50 years after everyone stops laughing. He said this in 1979. It's 2026. People are, largely, still laughing. But not everyone. And this is where the story gets weird. In the late 1990s and early 2000s, NASA's Institute for Advanced Concepts, a small, weird office designed to fund genuinely speculative research, commissioned multiple studies on space elevator feasibility. A researcher named Bradley Edwards produced a series of reports that concluded, roughly, that a space elevator could be built for around $10 billion using carbon nanotube ribbons, and that first cargo could reach orbit within 15 years of a serious program starting. Those reports circulated widely. They were serious, peer-reviewed, and taken seriously by a lot of aerospace engineers. And then, quietly, NASA's Institute for Advanced Concepts was defunded in 2007. The space elevator program never had a real successor. Edwards left NASA and started a private company. That company never built anything. I bring this up because there's a version of this story where the space elevator is a failed idea, and a version where it's an idea that was strangled in the crib by budget cuts and political priorities. Both versions might be true simultaneously. Now, here's where I have to tell you about the Japanese construction company, because this genuinely surprised me the first time I learned about it. Obayashi Corporation is a real, publicly traded Japanese construction firm founded in 1892. They've built skyscrapers, dams, and subway systems across Asia. And in 2012, they announced they were going to build a space elevator with a target completion date of 2050. I want to be clear. This wasn't a press release from a bored intern. Obayashi has an entire research division working on this. They've published technical papers. They've partnered with universities. They have a stated budget of about $100 billion. Their timeline calls for construction to begin in the 2030s, with the elevator becoming operational by 2050. The problem is, their plan explicitly assumes that carbon nanotube manufacturing will advance by roughly a factor of 10,000 between now and construction. They're not building with today's materials, they're building on the assumption that tomorrow's will exist, which is the same assumption every space elevator project has made since 1959. So let's actually try to answer the original question. If we were to attempt this today, right now, with 2,260 materials science, what would happen? We could produce, at best, a nanotube fiber a few meters long, with about 10% of theoretical tensile strength. To build a 100,000-kilometer cable, you'd need to splice roughly 20 million individual fibers together, end to end. Every splice is a weak point. Every splice reduces the effective strength of the cable. Every splice is a potential failure mode. Even ignoring splicing, the cable at 10% theoretical strength would need to be so thick at geostationary orbit, where the tension is maximum, that its weight below geo would exceed the tension the cable itself could support. The math doesn't just fail. It fails catastrophically. The cable can't hold itself up. And I haven't even gotten to the atmosphere yet. Here's a fact that gets weirdly little airtime in space elevator discussions. The lower atmosphere of Earth is a hostile place for a thin cable. Wind loading at various altitudes creates oscillations. Ice buildup at certain heights adds unpredictable mass. Aircraft collision risk is non-zero, but the real killer is lightning. A carbon nanotube cable is an excellent electrical conductor. Running one from the ground into the ionosphere creates, essentially, the world's largest lightning rod. Estimates I've seen suggest the cable would be struck by lightning multiple times per day. Carbon nanotubes handle current well in short bursts, but sustained high-voltage discharge causes localized heating, which weakens the material, which propagates damage. Every serious space elevator proposal has to solve this problem, and none of them fully do. The current best answer is put the base station on a mobile ocean platform near the equator in a low lightning zone and move it when storms approach. Which is a fine answer until you remember that the top of the cable is anchored 100,000 kilometers away in orbit and cannot exactly be dragged around like a boat. The base station can move a few kilometers. The problem is that lightning-producing systems are hundreds of kilometers across. You're not dodging weather, you're negotiating with it. Which brings us to the debris problem, and this one might be the actual deal-breaker. Low Earth orbit is currently home to something like 30,000 tracked objects larger than 10 centimeters, and an estimated 100 million untracked objects larger than 1 millimeter. Every one of them is moving at orbital velocity, roughly 28,000 kilometers per hour. A 1 centimeter piece of debris hitting a satellite has the kinetic energy of a hand grenade. A space elevator cable would extend through every orbital altitude simultaneously. It couldn't dodge. It couldn't shield itself. Every debris object in low Earth orbit would eventually intersect its plane. Modeling done by researchers at the International Academy of Astronautics estimated that an unshielded space elevator cable would be severed by debris impact within a few years of deployment. There's a counterweight problem, too. You need something like 1 million tons of mass anchored 100,000 kilometers above Earth to keep the whole thing taut. And every proposed solution to getting it there is somewhere between launch 1,000 of the biggest rockets ever built and capture an asteroid we don't yet know how to capture. I'm going to leave that one there because you can see where it goes. You start to see the pattern. Space elevators aren't a single technology problem. They're a stacked technology problem. You need breakthroughs in materials science, orbital debris management, atmospheric engineering, and megastructure construction, all of which have to arrive at roughly the same time. All of which have to work together. All of which have to survive real-world conditions we can barely simulate. And this is where I need to tell you about Michael Lane. In the early 2000s, a small company called Liftport Group tried to build a space elevator commercially. Their founder, Michael Lane, was a former Marine turned entrepreneur who genuinely believed he could raise the money to do it privately. He held conferences. He raised a few $1 million. He ran competitions where student teams built tether-climbing robots and raced them up cables suspended from balloons. For a brief window around 2005, Liftport looked like it might actually become something. Then it filed for bankruptcy in 2007. Lane relaunched it in 2012 with a Kickstarter campaign, this time proposing a lunar space elevator instead of an Earth one. The Kickstarter succeeded, barely, raising $110,000. Nothing was ever built. The website is still up. The last update was years ago. I bring this up because Liftport is the pattern for every private space elevator effort. The technology isn't there, the money isn't there, but the belief is there. Enough for people to give up careers, run companies into the ground, and keep trying anyway. There is something about this idea that attracts a very specific kind of optimist and consumes them. And I think that's important to name, because every technology I've mentioned, better nanotubes, debris removal, weather management, orbital construction, is being worked on somewhere by someone. None of them are impossible. Given enough time and money, all of them will probably happen. But the space elevator requires them to all happen at once and to be integrated into a single working system. and for that system to be economically justified against an alternative that's getting cheaper every year. Because while everyone was busy dreaming about elevators, reusable rockets happened. In 2010, the cost to launch 1 kilogram to low Earth orbit was around $10,000. As of 2026, on a Falcon 9, it's under $2,000. Starship, if it works reliably, could push that under $200 per kilogram. The economic case for a space elevator was built on rocket costs that no longer exist. There's a scenario, and I want to be honest that this is speculation, where the space elevator quietly becomes obsolete before it's ever built. Not because it couldn't work, but because rockets got cheap enough that no one needs it to. The graph of launch cost over time and the graph of space elevator readiness over time may never intersect. Rockets may just win. And this is the part that genuinely bothers me. Because the space elevator isn't just a cheaper way to reach orbit, it's a qualitatively different way. Rockets are violent, expensive, and require huge quantities of propellant. Elevators are quiet, continuous, and can operate around the clock. A working space elevator changes what humanity can build in space, not just how much it costs. It's the difference between an airport and a canal. One moves things faster, but the other moves things at a scale that reshapes civilization. Losing the space elevator wouldn't just mean losing a technology. It would mean losing a future that assumed we would have it. So back to the original question. Could we build a space elevator using only modern carbon nanotubes? No, not close. Not in the same universe as close. Modern nanotubes are somewhere between 1 and 5% of the weight of the material we would need, depending on how you measure. The gap isn't a matter of scaling up existing techniques. It's a matter of fundamentally solving the shear transfer problem, which no one currently knows how to do. And even if we solve that tomorrow, we would still need to solve debris, lightning, counterweight, and construction problems that each individually are civilization-scale challenges. The honest answer is that a space elevator, if it happens at all, is a late 21st or early 22nd century project. It requires material science that's still theoretical, orbital infrastructure that doesn't exist, and a global economic will that has to compete against rockets that are already good enough. But here's what I keep coming back to. Every barrier I've listed has someone working on it. Someone in a lab in Japan is trying to solve the shear transfer problem. Someone at ESA is designing debris removal systems. Someone at Obayashi is working out the construction logistics. Michael Lane, wherever he is now, is probably still thinking about it. None of them talk to each other, none of them are coordinated, and none of them have the budget to actually finish. But they're all still working. Which means the space elevator isn't dead. It's just being built by 100 different people in 100 different labs over a timescale none of them will live to see completed, and most of them don't even know they're on the same project. That's not a research program. That's a religion.